And now, after we covered linear SVM in all of its beauty and glory, we can go to the full case of SVM, the general. Let's quickly repeat what we already spoke about. So max margin classifiers given to classes A and B, data is a set of labeled examples, right? X is the features and Y is just a scalar label. And in this case, Bayesian decision boundary when distributions are known is defined as our posteriors, and where the difference of the posteriors is zero, is that surface in the multidimensional space at which the difference of the posteriors is zero is our decision boundary, which can also be represented as a ratio or log ratio, etc. Maximum margin hyperplane, we build it sort of guided by similar principles, by restricted optimal base classifier. When restricted to linear class, we'll get maximum margin hyperplane when we don't want to use any prior information at all and want to concentrate all of our distribution on each of those points on the figure on the right. So now, what to do when the data is not linearly separable in the support vector machine or just in general in any other method? And here's a suggestion. We can map each point into a higher dimensional space. From this two-dimensional space, we can construct by using some ingenuity or simple brute force library of functions phi, we can construct a mapping that takes our 2D picture, this one, into 3D, in the hope that in 3D the data becomes clearly linearly separable, although in 2D, going back, there is no way to put a line through those two classes and separate them. Well, you just need to either know how to construct those kernels or get lucky. If we use a polynomial kernel like here, so we take our x and y, or x1 and x2, and construct a three-dimensional space just using this kernel, then the data becomes separable, and now we can use a linear SVM, and it will succeed and we'll find this separating hyperplane. So this is kind of an interesting and maybe tedious process, right? We need to find a mapping, and appropriate mappings are hard to construct. What do we do in this case? So dimensionality can be many, even infinite, and we have to compute very expensive inner product, right? So first we have to map the data into feature space, then to compute, basically the trick is instead of computing inner product or doing anything with the original data points, we start working with transform data points or vectors, right? They are vectors in our case. For example, our inner product is now this inner product of feature mapped data. But this is also kind of expensive, right? What if this feature, as I say here, what is this feature mapping, or we want to map into infinite dimensional space? And by the way, radial basis kernel does map into infinite dimensional space, and you can see this if you wonder when you have time just try to decompose the inner product or that kernel into Taylor bases. So we can avoid first mapping into feature space and then computing the kernels by defining Hilbert spaces with kernels and using Mercer's theorem that will be next on the next slide. So a Hilbert space is a linear space that basically has an inner product defined. So what we can do, we can just define the inner product instead of defining the mapping. So for example, like our kernel is an inner product of the feature mapped vectors, but we can use our polynomial feature map and first map the vector x and then map the vector y and then compute their inner product. But in fact, and if you do the algebra, you will see that this inner product is nothing but just this expression. And this expression is much simpler to compute directly rather than first map each of the x and y and then compute the result. We can simply do this and be done if inner product is all that we care about, if we don't need to separately map into feature space. And the same here, the second order, another second order polynomial kernel, we can either first transform. Oh, wait. This is an example. Yeah, so what I'm doing here is I'm actually multiplying through this inner product, getting this and getting that, just to show you that it's the same. Either you first map into feature space and compute inner product, or just you compute inner product squared directly. The result is exactly the same, and this is much cheaper. So take a linear algorithm, replace inner products with kernels, and get a nonlinear algorithm as a result. If in your linear algorithm you don't separately have data entering as a data itself, not as an inner product. If your data enters into the algorithm just as an inner product, then this trick, the kernel trick, would work. Just replace all of the inner products of this form with inner products or kernels now in this form. And magically, you're now operating in the feature space, which is high dimensional and nonlinear. And with regards to support vector machines and linear support vector machines, the hope is that when we map into that feature space, we get to like the data becomes linearly separable. So let's check what happens to support vector machine when we apply the kernel tree linear support vector machine when we apply the kernel trick to it. So recall our original formulation on the previous slides in the previous section, where this is dual formulation. And notice this and that in the optimization problem and in the final classifier. The data and any samples, the new samples, the old samples, they only enter this whole process, the whole computation process, as an inner product. So what we can do, we can replace those inner products with kernels. And if we rewrite this in the matrix form, and by now in the class, you have to already understand that everything is better in the matrix form. So you can see how simple it becomes, and G is an actual matrix, it's called gram matrix. It's a matrix of inner products. XII is on the diagonal, and then XIJ is off the diagonal. But basically you can obtain this G matrix, which is n by n, number of samples by number of samples. That's what I was referring to in the previous episode about how uh, computational complexity of this problem grows quadratically and how bad really it is. That's why you need SMO, sequential minimal optimization methods, or SNS methods, or different tricks. But my point is, take your samples, all of your X sub I samples, and arrange them as rows in a matrix. So this is a d-dimensional matrix of n samples, X. And take X transpose, and when you multiply them through, you will get G, that G here. This G is matrix of inner products, and it's called Gram matrix. Okay, we're ready now. This beautiful dual formulation in the matrix form. Now we're ready to talk about Mercer's theorem. So what is a kernel? A function, K, that takes two vectors and returns a scalar is a kernel function if and only if it's symmetric, that is k of x and y equals k of y and x, and positive semi-definite. So positive semi-definite in terms of general functions, k will be defined as a vector, as an integral, but for us, it suffices that for all possible combinations of, like for all x and for all data points, this Gram matrix is positive semi-definite, which this just says it. Or from this, we know from linear algebra that it follows that minimal eigenvalue is no less than 0. Then the matrix is positive semi-definite. So easier said than done, because testing for positive semi-definiteness is difficult, and then symmetry is as well. So if you see a new problem, text classification or graph classification or chemical compounds classification, you need a new kernel technically, but it's very hard to just come up by following a guidebook with a new kernel. So basically coming up with a new kernel is an art, and back in the 2000s there were still lots of papers published that would introduce a kernel for this, kernel for that, because it was an art and people were devising a new kernel for each new application domain. Similarly, like now, lots of researchers are working in devising now this 2020, devising new architectures of neural networks for new domains they're applying deep learning to. So creating kernels is an art, but some generative rules can help. For example, an inner product, any inner product is a kernel. A constant is a kernel. Kernel product is also a kernel. For all functions that map vectors to scalars, product of those functions is also a kernel. Non-negatively weighted linear combination of kernels as a kernel, and a few more rules that you can use to construct your kernels out of already existing kernels, which are the popular polynomial kernel and the radial basis kernel, and others, a few others. So beautiful, but kernels do not guarantee linear separability, unfortunately, even though they strive for that and can push us into nonlinear domain. But still, no, no, no. Well, it is the same as with your neural networks. The neural networks, deep learning, can be thought of as learnable kernels is a complicated or complex nonlinear mappings of data, and then you apply on top something like a max margin classifier or rather logistic regression. The only point is that when you are manually picking a kernel by using some rule of thumb or I don't know, some superstitious feelings and prior experience, then you can make mistakes and pick a kernel that always worked to you for you, but today doesn't work. And then what to do? It's not separating the data. Is not separating. In deep learning, you kind of training the kernel to separate the data. So that's why it's so popular because it is so powerful and it replaces one art, the art of picking correct kernel, with another art, the art of training deep learning. But in any case, so not linearly separable data even after we executed all of our artistic abilities and selected the kernels that we thought would work. Or we even cheated. We went to a cluster of supercomputer and ran a hyperparameter search, sifting through all possible kernels and still didn't find one that would separate the data and return a sparse solution where only a few supports are remaining. What to do? Well, in this case, so far we talked about something called hard margin SVM. Let's talk about soft margin SVM. Let's introduce slack variables. Some slack variables chi larger than 0 or non-negative. They can be equal to 0. This way will allow mistakes. So at first we wanted everything to be either on this side greater than 1 or on that side, right? And the label took care of the sign. But now we're saying, okay, well, sometimes mistakes happen, so we allow for each particular sample, we allow a slack variable. So it could be a little wrong. We are saying, okay, you can be a little wrong. So there's this teal class or blue class, and for everything that's correctly on the correct side of the hyperplane, constraints are inactive and slack variables are also inactive. For the same for the other side, slack variables and constraints are inactive for correctly classified correctly classified samples. But for something that is still correctly classified, but within the margin, slack variable is less than 1. But for something that is incorrectly classified, this additional slack variable that we just introduced is greater than 1. So given that when we have this, okay, and we plug this into our dual formulation and do the math, beautifully and surprisingly, the slack variables fall out, and we end up with the so-called box constraint right here. As you see, alpha Lagrange multipliers are constrained to a box because each of the alphas is within between 0 and C now, and that is, if you think of alpha as a three-dimensional vector, that's just, it's within a box with a side C. It has to be inside of this box. So by introducing slack variables, we went from just non-negative Lagrange multipliers to box constraint like Lagrange multipliers, where C, this slack or the box constraint hyperparameter, needs to be determined somehow, either by cross validation that we will discuss later, or some other more complicated or more actually specialized methods, such as incas. Not going to discuss. We already spending a lot of time on support vector machines in this class. Uh, this is a lengthy lecture. Support vector machines are extremely important and fruitful in terms of bringing a lot of ideas to the field of machine learning and actually being powerful, uh, dominating the field for almost 20 years and still being irreplaceable, I would say, in some tabular data classification and some simple data classification that is not big data and not sensory. Um, okay, what next? Let's now see how this same addition affects the primal formulation. So for the primal formulation, remember that we were maximizing the norm of the vector normal to the hyperplane that define this hyperplane. But now we need to maximize this whole expression. Yes, this is the weight of the slack variables, and the sum is larger the more mistakes we have. If we don't have any mistakes, this goes to zero, and then we're back at the original hard margin primal formulation. When do we have no mistakes? When the data is linearly separable. So if we want to penalize mistakes with infinite penalty, remember that when we defined our primal formulation in the beginning, the constraints were hard. They just had to be satisfied. That's like infinite penalty if you violate the constraint. So if we put C to infinity, then we'll get exactly the hard margin SVM of the one we originally defined. So like this example shows us, the higher the C, the like closer the solution is to the max margin, and the smaller the C, the hyperparameter, the more we allow, like the wider is overlap of the margin with the data. Um, okay, so what did we learn? Take home points. Advantages of SVM. Quadratic programming with single optimum is very efficient, although still quadratic. We do need linear methods or sublinear methods for big data. Sparse solutions based on supports. Sparse is good and easy to handle. And when we get just few supports, prediction is actually blindingly fast. And that's important in practice in production. And then because of the large margin, we get great generalization, unlike other methods. Another thing, okay, well, let's talk about disadvantages first. So sensitive to noise and outliers in data. Just start adding outliers and the solutions, even with soft margins, will be affected. Um, Making or choosing kernel for the task is an art, and that is actually the largest problem with support vector machines, and that's why deep learning is uh, has replaced support vector machines, at least in the discourse, popular discourse in academia now. Well, another problem is dependence on soft margin hyperparameter C, because now you need to estimate it somehow. But there is no hyperparameter free learning, as they used to say. So I wouldn't worry too much about that. Notice one thing. when we talk about separating hyperplane, and let's assume oh, no, yeah. So we wanted non-negative answer when we classified everything what we trained and found a separating hyperplane. We are finding separating hyperplane either when we use a perceptron algorithm, or when we use logistic regression, or when we use support vector machines. The family of the classifiers are H from our first lectures. The hypothesis set is exactly the same. We're looking for just one separating hyperplane among all possible hyperplanes. But the learners are different. We have covered so far at least three different, widely different algorithms: logistic regression algorithms, support vector machine algorithms, and perceptron. They use different objective. They're optimized different objective function, and they solve like this is a tricky thing. Pay attention. Um, because when you're solving a problem, when you're applying some numerical method or some machine learning method, usually you have real world problem, and then it's easy to fall into a mistake, into the following error, thinking that the algorithm is solving your problem. The algorithm is actually optimizing some objective function. And it is your task as a researcher, as an engineer, as a scientist to figure out which objective function fits your problem best. Machine learning doesn't solve this problem so far. Well, but wait a little bit and we will have general intelligence, general artificial intelligence, and then things will become much easier, I promise. Thank you.